Okay, well now this is a very unusual situation because the recordings that we have been using up until now were actually recorded 2 years ago. And one of the recordings we had technical problems with, and so I'm having to re-record this 2 years later. So we're in a little bit of a time warp here. And I'm also lecturing to an empty classroom because it's in the middle of summer. But I've got a trusty camera operator here, Josh, who actually was in the course last time, is manning the camera for me. So he can be our student body. So thanks for doing this, Josh. Now, actually, I want to take this chance to explain a little bit about how these recordings are done. So all the recordings up until now have been done using the 4th edition of computer systems. Since then, the 5th edition came out. In fact, it came out right in the middle of this, the previous semester. And so here's what we're doing. So we have chapter 10, 11, and 12. And chapter 10 is on combinational circuits. And chapter 11 is on sequential circuits. And chapter 12 is on computer organization. And here's how these lectures are all working and how they're tied into the book. As it turns out, these two chapters are virtually unchanged between the 4th edition and the 5th edition. So this is like 4th, 5th. And so what we're doing is I'm using the slides for the 5th edition to compose the videos, even though when the lectures were first given, they were the slides for the 4th edition. And, but they're basically the same, except for one small problem. You'll notice from here on out, in chapter 11, when I refer to a figure number, it won't match the figure of the slide from the 5th edition because I was lecturing with the 4th edition, but using the slides for the 5th. So we threw in a little extra slide there, and so the slide numbers don't match up. So anyway, that's a little explanation in case you're a little confused about when I say one thing and the slide number is something else, figure number is something else. On the other hand, chapter 12, computer organization, there was a substantial change between the 4th and the 5th edition. And what we're going to do in this sequence is we're going to use just the 5th edition, and we are going to describe the computer organization of the PEP 9 computer. And so that sequence of lectures was recorded just a few months ago with the new edition. So that's a little bit of an explanation about how all this stuff is working. But the best thing to do in viewing the lectures, going through this course, is to use the 5th edition. Even though I lectured with the 4th here, it's basically the same as the 5th. And this is PEP 9. In the 4th edition, we used PEP 8, but that doesn't come into play here. It only comes into play in the chapter 12. Okay, so that's a little description of our predicament. And here's another little predicament we have. 2 years ago at this time, 2 years plus a few months at this time, there was a homework assignment due. And unfortunately, because we can't use the lecture, I don't know what questions there were. So, you know, usually I say, well, are there any questions about the homework? Of course, now we're lecturing to an empty classroom. There's only one student here. And so, Josh, are there any questions about the homework? No. So what I'm going to try to do is I'm going to try to anticipate a question. In fact, as I recall, let's come over here, focus over here. What was due were a few exercises from chapter 11. I think exercises 2 and 3. And in anticipation of what some of the questions were, I thought I would get you started on exercise 3, just trying to anticipate what some of the questions might be. Now, and so remember in class last time, 2 years ago, we had just talked about the master-slave SR flip-flop. And remember, this was the master stage, and this was the slave stage. And this exercise 3 is a question about that construction, about this master-slave circuit. And actually, the first 2 parts, parts A and B, are actually given in the back of the book. The solution is given in the back of the book. So I thought I'd just get you started and describe how this works in case you might have a question about it. Now, if you read the exercise, it says, define the following points in figure 11.10, and it says A is the output of the top master AND gate. So here, let's take a look. So it said A was the output of the top master AND. So this is the master, this is the slave. So A is this point right here. Are you with me? And then it says that 2. B is the output of the bottom master. So B is this point. Yeah? And then it says, the book says, C is the output of the inverter. So here's the inverter. So that's point C. And then D is the output of the top. E is the output of the bottom. D and E, right? So those are the points. And then it said describe the state of the circuit at these various points for 4 different times, T1, T2, T3, and T4. So you remember in class last time, we defined those points like this. When a clock pulse comes along, it's not instantaneous. It goes up gradually. And then when it goes down, it's not instantaneous. It goes down gradually, right? And so those 4 times are these times right here. So here's T1, T2, T3, and T4. And you remember these correspond to these thresholds, these voltage thresholds. This is threshold V1, and this is threshold V2. All right? And so to do this homework assignment, what you need to do is construct a table that starts off like this. We have the points A, B, C, D, E, A, B, C, D, E, R2, S2, Q, and Q bar. R2, S2, Q, and Q bar. Now what were R2 and S2? R2 and S2 are these. These were already given in the original. This is R2 and this is S2. All right, this is S and R. So this is the internal R. This is the R of the slave, and this is the S of the slave, the S input to the slave. All right? And then it says, and then we have this A is before T1. This one's before T1, and this is between T1 and T2. So that's row B, right? And then it says, construct a table that shows the values of A, B, C, D, E, R2, blah, 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 during each of the following intervals, assuming 0 gate delay. Now, what are the initial values? Okay, and so now the problem also says that suppose SR equals 1, 0, and Q equals 0. So suppose SR equals 1, 0, and Q equals 0. And then it asks, the exercise asks to fill out the values of the voltage, the signals at each one of these points in the circuit before T1, between T1 and T2, between T2 and T3, between T2 and T4, and after T4. So let's do the first couple just to get you started. All right, now, first of all, before T1, the clock is 0, right? So this is 0. Yeah? And now, 0, this clock, the 0 and anything means the output of the AND gate must be what?
0.
Yeah, so we have 0, 0. Are we good? And now we know that Q and Q bar are the inverse of each other. So if this is 0, this has to be 1, right? And this, and also we know, coming back to the clock, we know if this clock is 0, then 0 inverted, because it's down here, 0 inverted, this has to be 1, right? So this is 1. Are we good? So far, so good? Now what about D and E? So let's figure out now what the signal at point E would be. Well, what we have is we have a 0 coming in here, right? So if E were a 1, it would be 0 or 1, inverted would be 0, but it's not, it's 1, right? So if we have a 0 coming in here, this has to be 0, because 0 or 0 is 0, inverted is 1. All right, and now, now that we know that this is 0, now this is 0, and now this is 1, right? So this 1 coming in here is going through this AND gate. So S2 can't be 1 because 1 and 1 would be 1. So S2 must be 0. So this signal must be 0. Are we good? But we know that this is the Q and the Q bar, the Q and the Q bar of the master, and so we know this is the opposite. So this is 1. And now can we figure out what's at D? Well, now we have a 1 coming in this AND gate, a 1 coming in this AND gate, so D must be 1. I think we have all of our points, right? Okay, so D is 1, E is 0, R2 is 1, S2 is 0, Q is 0, and Q bar is 1. And this row is also in the back of the book, one of the solutions. Now let's just take a look at what happens between T1 and T2. I think this will be very instructive. So check this out. At T1, this V1 threshold hits. So looking at figure 11.10, we see that that's the threshold for which device? The AND gates to the master or the inverter? Which one is it? Is the threshold T1, is this threshold V1 that gets crossed at time T1, is that the threshold of those AND gates or is it the threshold of the inverter? Of the inverter. So what that means is that at time T1, this flips. Are you with me? So boom, so underneath this we'll do blue. So this goes to 0, right? Now these AND gates, the 0 from the clock hasn't hit this threshold. Are you with me? So these AND gates still have these zeros coming into them, right? But what happens when this flips to 1? What happens? Now what happens? When this flips to 0, what happens? Now this 0 is going into these AND gates. So what happens to signal D and E? They both become 0. E was already 0, but this one stays 0. But now we know what happens when this goes to 0, 0. When this goes to 0, 0, the state of the slave doesn't change because everything is consistent. We still have 0, 1 being consistent, right? And nothing changes here. So what should happen here? This should be what? A, B. We never did figure out what A and B were. Oh, well, we said it was 0, but we didn't write it down. So here, A, 0, 0. And so what happens now, we said that this threshold didn't change, so A and B stay 0, 0. So this is going to be 0, 0, and then C and D are what? Where's C and D? C changed to what? 0. D changed to what? 0. E stayed 0, and these stayed 1, 0, and the Q and the Q bar stayed 0, 1. So there you have it for that one. And we can double check the back of the book for just these two rows. And sure enough, 0, 0, 0, 0, 0, 1, 0, 0, 1. 0, 0, 0, 0, 0, 1, 0, 0, 1. All right, and then you can do the analysis for the rest. All right, good deal. Now, at the end of class last time, 2 years ago, we had gone through all of this stuff. We looked at here we looked in figure 11.13, we looked at the characteristic table of the SR flip-flop, and we noticed that there were 4 possible combinations of S and R. If SR is 0, 0 and a clock pulse comes along, there's no change. If SR is 0, 1, S stands for set, R stands for reset. So if SR is 0, 1, that's the reset condition. And so regardless of what the input is, the Q at time t plus 1 is 0. And then if SR is 1, 0, S stands for set, so that sets Q to 1. And then what happens if SR is 1, 1 and a clock pulse comes along? Do you remember what we said about that?
We don't know.
Yeah, we don't know. It's unpredictable. About half the time it could come down one way, about half the time the other way, and it's unpredictable. So we don't know what that is. And then what we did in here in 11.14, we drew the finite state, the state transition diagram for the SR flip-flop. All right, now, next on the agenda is to introduce, there are actually 4 common flip-flops that are used in sequential circuit design. The SR is the set reset, the JK is the set reset toggle flip-flop, the D is the data or delay flip-flop, and T is the toggle flip-flop. And we're going to learn how each one of these works, and we're going to learn how to build them. But the fundamental one, the one that we build from just and OR gates and inverters, is the SR flip-flop. What we have to do is we have to add circuitry to the SR flip-flop to construct the other ones. We're going to learn how to do that. So here's the thing. The SR flip-flop, which we've analyzed in infinite detail now, using this master-slave principle, that's the basic building block. And so what we're going to do is we are going to learn a design procedure that we're going to actually generalize a little bit later. And this design procedure, there's a set recipe, a set way to do this design, and it will show us how to make one kind of flip-flop out of another one, using one to build the other. Now, before we take a look at this, let's go back to figure 11.13, this characteristic table, and let's see, what does this table tell us? This table tells us, given what does it tell us? It says, given the state at time t and the S and R signals at time t, if a clock pulse comes along, it tells us what the next state will be. Now, this characteristic table is used in analysis. But now what we're going to do is we're going to introduce the concept of design. Now with design, what's given and what is to be determined is different from what's given and what is to be determined in analysis. And so while this table is important to characterize what we know about how a flip-flop works, what we need is a different kind of table in order to do design. And the name of this table is it is called an excitation table. So, according to this slide, the excitation table is a design tool for constructing circuits from a given type of flip-flop. In order to build a flip-flop, we want it to behave a certain way. In other words, we want to specify the transition Q at time t to Q at time t plus 1. And what we want to know is what must the inputs be in order to make that transition. So here, with an excitation table, what's given is Q at time t and Q at time t plus 1. And we want to know the input. A characteristic table is given what? Given the state and the input, what is Q at time t plus 1? You see how that works? So here, what we're going to do is, let's see if we can, now what we're going to do is we're going to construct the excitation table for the SR flip-flop. Now check this out, you guys. All excitation tables have how many rows? Because look, here's Q at time t, Q at time t plus 1, all right? And what we want to know is what is S at time t and S, sorry, it's the SR flip-flop, S at time t and R at time t, to make that transition. Now tell me, how many rows is this table going to have?
4.
4. Why? Because there's 4 possible transitions. You can transition from 0 to 0, or from 0 to 1, or from 1 to 0, or from 1 to 1. Are you with me? And now the question is, what must S and R be in order to make these transitions? So look, if you want the state at time, if the state at time t is 0, and you want the state at time t to be, at time t plus 1, to also be 0, what do you have to make S and R to be in order to do this? You know, this is kind of like learning subtraction. A, you know, when you were a little kid, A plus, 5 plus what is 8? You know? So here's the thing. This to this, what must this be to make this be that, to have this transition? Well, how can you do this? What must S at time t and R at time t be in order to make this transition? Well, there's a couple possibilities. Could be what?
0, 0.
Could be 0, 0, because what does the 0, 0 condition? It's the unchanged condition. But there's another possibility. It could also be what?
0, 1.
It can also be 0, 1. Now, why could it be 0, 1? Because 0, 1 is the reset condition, right? But wait a minute. We can't have 2 things here. We only have to have one. So look, what do we know about this? S must be what?
0.
R could be what?
Either 0 or 1.
0 or 1. That means we don't what?
We don't care.
We don't care, but we know how don't care conditions work, right? So 0, 0 or 0, 1 means what? Another way to write that is what?
0x.
0x. And now we can use our don't care condition like we've been doing it with our Carnot maps, which we will do. Are you with me? Now, how can you make a transition from 0 to 1? You have to do what?
You have to set.
You have to set it, because Q set. So what's the set condition?
1, 0.
1, 0. So if S is 1, R is 0, that's the set. So that's how to set. And in order to go from state 1 to state 0, you have to do what to this flip-flop?
Reset.
You have to reset it. So the reset condition is 0, 1. But now, if it's 1, 1, you have a choice. You could either do what? You could either do 0, 0, which is the no change, or you could do the what?
You could set.
You could set, and set is 1, 0, right? Well, what this is telling us is that R must be 0, right? But S could be 0 or 1. So that means what? That means X0. So this is the excitation table. So let's see if we got it right. Yep. So do you see how to construct the excitation table? It comes from knowing the rules of what the conditions are for S and R. Okay, and now on to our main task for the day, the JK flip-flop. Now here's what the JK flip-flop does. We know that the SR flip-flop has an undefined condition, namely when SR is 1-1. It's unpredictable what the flip-flop does. What the JK flip-flop does is it resolves that undefined condition. And it's like this. Here's SR, here's JK. So what happens is J corresponds to S and K corresponds to R. Are you with me? And for 3 of the conditions, JK and SR are identical. In other words, if JK is 0, 0, what condition is that?
No change.
No change. If JK is 0, 1, what condition is that? That's the reset. If JK is 1, 0, what condition is that? Set. But now, if JK is 1, 1, something specific happens. That is the toggle condition. All right? So JK equals 1, 1 toggles from one state to the other. And it resolves the undefined condition. So here in figure 11.16 is the characteristic table of the JK flip-flop. Notice that if JK is 0, 0, that's the no change. If JK is 0, 1, it's the reset. If JK is 1, 0, that's the set. But now, if JK is 1, 1, that's the toggle condition. Now here's the thing. Now what we're going to do is we're going to build this flip-flop. And there is a certain design procedure for, there is a specific design procedure that we're going to learn of how to build one flip-flop out of another one. Okay? So, and here's, before we look at this summary of what we have to determine, let's take a look here at figure 11.17. In figure 11.17, we have we are defining the problem that we have to solve. We are defining the circuit that we must design in order to make a JK flip-flop out of an SR flip-flop. Now, this is now what is a black box? A black box shows you what?
It shows you the inputs.
The inputs and the outputs, but not how it's built, right? Not what's inside. Okay, so now, if you look at this dashed line in figure 11.17 and just ignore everything that's inside there, that looks like a JK flip-flop because we have J and K coming in from the left, we have the clock coming up from the bottom, and we have Q and Q bar going out. Are you with me? But now, so that corresponds to this in figure 11.16, that corresponds to figure 11.16a, that block diagram. See, we have JK coming in, Q and Q bar coming out, and we have a clock. Okay, so the black box is actually figure 11.16a. Yeah? This is a little bit whiter. So this is showing, so what happens is inside of a JK flip-flop, there is an SR flip-flop. Are you with me? And the way we make this whole thing act like a JK is we stick a combinational circuit in the front of the SR flip-flop, and we have our J and K going into that combinational circuit. Also, now there's some feedback. You see there's some feedback from the Q of the SR flip-flop around into the combinational circuit. Now you understand that inside the SR flip-flop, there's this. Figure 11.10. Are you with me? So all of that stuff is inside the SR flip-flop. Yeah? So, and we have this, we have cross-coupled, we have some feedback connection in the master, we have some feedback connection in the slave, we have master-slave, we have blah, blah, blah. All that stuff is inside there. Right? So let's go back here. Just to remind ourselves of where all the circuitry that's involved. Okay, so if we go to figure 11.17, inside that SR flip-flop is all that master-slave stuff. Yeah, with those cross-coupled feedbacks. But now there's an additional feedback now that we're taking from outside the SR flip-flop into this combinational circuit. Now, So you see, our task is to design that combinational circuit. Now, I ask you, the block that says combinational circuit, how many inputs does it have?
3.
It has 3. J going in, K going in, and Q going in, right? And how many outputs does it have?
2.
2. So I ask you, before we even get started, if we are to design a 3-input, 2-output combinational circuit, what are the Carnot maps going to look like? Well, first of all, how many Carnot maps will there be?
There'll be one for each output.
Yes, there will be a Carnot map for the S output and a Carnot map for the R output. Now you understand the S output of the combinational circuit is the input to the SR flip-flop, and the R output from the combinational circuit is the R input to the SR flip-flop. So there will be, we have to design a circuit for S, and we have to design another circuit for R. Are you with me? And so now the question is, how do we do that? Well, we have a little step 1, step 2, step 3 bullet point chart here that outlines our task. So step 1, given Q at time t, J at time t, and K at time t, list the desired state after the transition Q at time t plus 1. Step 2, given Q at time t and Q at time t plus 1, use the excitation table to list the required input for S at time t and R at time t. And then step 3, use Carnot maps to design minimized 2-level combinational circuits for S at time t and R at time t. Now this sounds really complicated, but it's really not. I mean, it's blah, 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 blah. But once we get the concepts down, it's really not that difficult. So let's see now if we can go through the steps of this design table very systematically and design our JK flip-flop. So step 1, given Q at time t, J at time t, and K at time t, list the desired state after the transition Q at time t plus 1. So here we go. Let's start. Let's see if you can do this without peeking ahead at the slides. Okay, so we're going to have Q at time t, J at time t, K at time t. All right, and then we're going to also list on this Q at time t plus 1. So let's start with this. There will be some more. All right, now how many rows are we going to have? First of all, well, there's 3 possibilities. I mean, how many combinations of 3 do we have? There's going to be 8. Well, 8. Yeah, 2 cubed, right?
Yeah.
Okay, so now we're going to do something. We're going to do 0, 0, 0, 0, 0, 1. Now what we're going to do is 0, 1, 1, 0, 1, 0. Now do you see, does this look? Why didn't we do 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1? Why didn't we do that?
It'll be easier to load into the Carnot.
Yeah, because we're looking ahead. We're going to have to transfer this to the Carnot map. So we're looking ahead so that transfer will be easy. And then we can have 1, 0, 0, 1, 0, 1, 1, 1, 1, 1, 1, 0. All right? Now, we'll go around the room. Okay, now, let's think a minute. If JK is 0, 0, what condition is that?
No change.
No change. So if this is 0 before, after it must stay what?
0.
0. 0, 1 is the what?
Reset.
Reset. So regardless of what this is, this has to be what?
0.
1, 1. Now, with the JK flip-flop, 1, 1 is going to mean what?
Toggle.
That's toggle. Well, if the original state is 0, then to toggle it means to flip it. All right? So this state will do what?
It'll flip to 1.
Flip to 1. And 1, 0, what is that? What condition is that? JKSR set. So set, regardless of what this is, this has to be what?
1.
1. Is everybody following us? Unfortunately, Joshua's a really good student, and so we won't have any challenges probably. Okay, so 0, 0 is what?
That's the no change.
No change, so stays 1. 0, 1 is the what? JKSR reset. So regardless of what this is, 0. Are you with me? Did I do that right? 1, 1 is the what?
That's the toggle.
That's the toggle. So this, what happens to this state?
We flip it to 0.
Flips to 0. 1, 0 is the what? JKSR set. Reset. Set. So this is the set. So regardless of what this is 1. Right? Now, you guys, here's the question. What must S at time t and R at time t be in order to make this transition? So now look, this is kind of tricky. So now what we have to do is we have to look at the initial state and the final state. Are you with me? And we have to go back to that excitation table and ask ourselves, what must S and R be in order to do this? Well, do you remember what we had on row 0, 0? It could either be, how do we reason that?
It could be a no change.
It could be a reset or a no change. So a no change is 0, 0. The reset was what?
0, 1.
0, 1. So that was what?
That's 0, don't care.
0, yes, 0x. Now we could just look at that table and just read off. So what was the 0, 0? Oh, that's another 0x, right? And what was 0, 1?
That's just a set.
So that's 1, 0. And then 0, 1, that's a set. 1, 0. Are we good? 1, 1.
That's either
Now, this is either a
set or a no change.
yeah, if we had our excitation table in front of us, we wouldn't have to think about this. We could just read it off. Okay, but what is it?
It's going to be x 0.
X 0? Right. And this is what? A reset.
Yeah. So that'll be a 0, 1.
Right? A 1, 0, transition 1, 0 is what?
That's the same thing. Should be a reset.
And this is what? 1, 1.
Either a set or a don't change. So x 0.
X 0. Are we good? Let's see if we got it right. Yep, we did it right. We were actually cheating. It was up there when we were doing it. Anyway, don't tell. All right, anyway, this is good. Okay, now what we have to do is we have to construct the circuit. So now we're going to have one Carnot map for S and another Carnot map. We have to design a circuit for S and a circuit for R. All right, so here we go. Let's do the Carnot map for S. So we'll do the Carnot maps here. Okay, so let's see how we want to label these. So this one is S equals, and this one is R equals. And this is going to be Q, and this is 0, 1, and this is going to be JK. Is that right? Yes, and this is 0, 0, 0, 1, 1, 1, 1, 0. So this is JK, 0, 0, 0, 1, 1, 1, 1, 0. This is 0, 1. And now is all we have to do is transfer these over. So now, when Q is 0, 0, 0, 0, S is 0, 0, 1, 1. So when Q is 0, 0, 0, 0, S is 0, 0, 1, 1. Now you see how easy that was to transfer them over? And then this, when Q is 1, 1, 1, 1, S is X, 0, 0, X. So when Q is 1, 1, 1, 1, S is X, 0, 0, X. Are we good? Let's transfer the ones over for the J, for the R. Okay, so when Q is 0, 0, 0, 0, R is X, X, 0, 0. So when Q is 0, 0, 0, 0, R is X, X, 0, 0. Now, don't ever write the zeros down on your Carnot map. It gets way too crowded. And when Q is 1, 1, 1, 1, R is 0, 1, 1, 0. So when Q is 1, 1, 1, 1, R is 0, 1, 1, 0. Actually, as it turns out, those don't care conditions don't come into play here, right? Because how would we minimize, how would we group these?
We can just group those two ones together.
Yeah. Okay, and we don't, I mean, it wouldn't make any, it wouldn't bias anything to try to cover any of these x's. And furthermore, we could cover this one with this x, but why do that when this one has to be grouped with this one anyway? So what's this? Like that. And now we can just read these off. Yeah. So if we read this off the Carnot map, this is for what row? This is the Q equals 0 row, right? And what are the right two columns?
That's going to be J equals 1.
J, yeah. So this is Q bar. This is
Q naught J.
Yeah, Q. Yeah, J. Yeah, J Q bar. And this one, this is the Q. And now what are the two middle columns? The two middle columns are K, right? Mm-hmm. So this is KQ, is that right?
Yeah.
All right. And now if I were to ask you to write this up, how many gates, Oh, by the way, if Q is an input, we would need an inverter here. But look, let's go back to this figure. Let's go back to figure 11.17. We showed just Q coming in. So we could just have that Q coming in and then put an inverter there. But why put the inverter there? Because we already have automatically, as one of the outputs of the SR flip-flop, we already have Q bar, you see. So we don't actually need to use Q and then put an extra inverter there. We can save ourselves a gate, we can save an inverter by using the Q bar. So you might, but I don't like to draw the Q bar going into that combinational circuit. It would make it look like a 4-input circuit, but it's really just a 3-input circuit, right? But anyway, so here, okay, so now here, in figure 11.20, ta-da, is our design. Here is how you build a JK flip-flop out of an SR. And notice that what happens is the S output is J and then the Q bar feeds back from the SR flip-flop, right? So there's the J and Q bar here, okay? So this J and Q bar is that. And then this R is K and Q. So let's go back to the figure. So K and so the Q feeds back into the AND gate with the K. And so this circuit will behave exactly like we want it to behave. In other words, and let's think about it. If JK is 1, 1, then what happens? Then Q is fed back directly into R, and Q bar is fed back directly into S. So if Q is 1, then the input into the S and R will be what?
be,
If Q, let's think about this. If Q is 1, what will be the input of S and R, of SR?
It'll be 0, 1.
It will be and what is the 0, 1, what is the 0, 1 condition?
It's the reset.
It's the reset. So then after 1 clock pulse, it'll be reset. On the other hand, if Q is 0,
Then it'll be 1, 0, which is the set.
which is the set. And so it'll set. So again, it will toggle. See how slick that was? You can maybe figure that out and ad hoc, some sort of ad hoc way, but this is a systematic way to do it. Okay, so there you have it. We built a JK flip-flop out of an SR flip-flop, and what we'll do next time is we will learn how to construct, we will learn about the other flip-flops, the D and the T, and we will use the same design procedure to build them as well eventually. All right, good deal. See you 2 years previous from now, and when we get to chapter 12, I'll see you whenever. So we're doing lots of time travel here. Okay, thanks so much, Josh, for manning the camera for me with this empty classroom. Oh, shoot.
What?
Oh, no, wait. Is this correct? Okay, so we just discovered that I'm not sure how I'm going to edit all this. All right, so now the next thing is between T1 and T2. We're not going to have enough time to finish the lecture. We're going to spend all the time on this hypothetical question that nobody had. Okay.